Heap is a data structure that allows us to store a collection of elements and quickly perform the following operations. We can insert an element, we can return the extreme element, that is either the maximum element for a max heap or the minimum element for a min heap. And we can also remove the extreme element, that is again either the maximum for a max heap or the minimum for a min heap. So the first important thing that you should know is that there are two different types of heaps. The first one is a max heap. In a max heap, we can insert an element, we can return only the maximum element, and we can remove only the maximum element. We don't have access and we cannot remove the minimum element in a max heap. Let's see an example of a max heap. Suppose it is initially empty. We can insert a value like 10. Then we can insert another value like 7. We can return the maximum value, which is 10. We can remove the maximum value, so we remove 10. Now our max heap consists only of 7. Then let's say we insert 2. We can return the maximum, which is 7. We can insert another 7, so yes, there can be multiple equal elements in a heap. If we want to return the maximum, either one of the 7s is fine, so we will return 7, and then if we want to remove the maximum, it will remove either one of the 7s. The second type is a min heap, where we can insert an element, we can return the minimum element, and we can remove only the minimum element. We don't have access and cannot remove the maximum element in a min heap. Now let's see how a heap works behind the curtains. The heap is a complete binary tree that satisfies the heap property where any given node is either always greater than or equal to its child node or nodes for a max heap, or it is always smaller than or equal to its child node or nodes for a min heap. A complete binary tree is a binary tree in which all the levels are completely filled except possibly the lowest one, which is filled from the left. But let's see an example. Let's see how the max heap will look like for this set of elements. In a max heap, the largest value always lies in the root node, so here we have 12. Then, the next two largest elements will be placed in the root's child nodes. So let's say 9 is placed in the left sun and 10 in the right sun. And the smallest 4 elements are going to be placed in the leaves. Again, the order doesn't really matter, they could have been placed like this. All that's important is that heap property to be satisfied and the max heap will be valid. Now let's see how the min heap will look like for the exact same set of elements. In a min heap, the minimum element will always be placed in the root node, so here is 2. The next two smallest elements, 4 and 6, are going to be placed in the root's child nodes, and the rest of the elements, the greatest ones, are going to be placed in the remaining nodes. Again, order is not important. Now let's see how this binary tree is being changed behind the scenes each time we perform an insert or remove operation. Let's say we start with an empty min heap, and the first operation is to insert 10. We are going to create a new node of value 10, which is now going to be the root of the heap. Each time we insert a new value, we are going to create a node which stores that value and insert it at the end of the lowest level. And if the lowest level is already completely filled, then we are going to create a new level. Let's insert the value 9. We will create a new node of value 9. The lowest level is level 0, where we have the root. This level is completely filled. So 9 is going to be the first node of the next level, which is the left sun of the root. Then, each time after we insert a new node in the heap, we have to make sure that the heap property is still satisfied. For a min heap, this property states that each node should have a value less than or equal to its children. In other words, each node should have a value greater than or equal to its father node. Does this hold true here? No, 9 is less than 10. So what we are going to do is swap the values in these two nodes. Now 9 is the root and 10 is its left son. And we have a min heap. Now let's insert the value 12. The lowest level is level 1, which is not completely filled. So we will create a new node of value 12, and this node will be the right son of the root. Does this new node satisfy the property of the min heap? It does. 12 is greater than or equal to 9. So our binary tree is still a min heap, no changes needed. Let's move on and insert the value 7. The lowest level is level 1, which is now completely filled. It has two nodes. So our new node will be the first node of level 2, which is the left son of node 10. Does this node satisfy the min heap property? It doesn't. 7 is less than 10. So what we are going to do is swap the values in these two nodes. Is our job done yet? No. One swap operation might not be enough. We should still continue checking if the node where value 7 is placed satisfies the min heap property. And it doesn't. 7 is less than its father 9. So we are also going to swap the values in these two nodes. Now 7 is the root. It doesn't have a father, so there is no condition to be checked. So our job is done now, and this is indeed a min heap. Let's say we insert value 2. The lowest level is level 2, which only has one node out of the 4 nodes that it can have. So our new node will be placed at the end of this level, which means it will be the right son of node 9. And we start checking. Does our node satisfy the condition? It doesn't. 2 is less than 9. So we will swap these values. We check again. Does our node satisfy the condition? It doesn't. 2 is less than 7. So we swap these two values. Now it became the root, so is no condition to be satisfied, and this is indeed a valid min heap. So in the general case, we will always insert a new node in the heap, and for as long as the current node's value is less than the father's value, we are going to swap these values and continue the algorithm from the father node. We will stop when either the current node is greater than its father or when it became the root of the tree. So in the worst case, the number of steps that we perform in order to make sure that we have a min heap is equal to the size of the path between the new node and the root, which is at most the height of the tree steps. Now let's see what happens behind the scenes when we remove the minimum element from a min heap. We should technically remove the root node, but this is not easy, because removing the root node leaves us with two binary trees, which we will then have to merge in a smart way in order to obtain a min heap. We will do something a little smarter. Because removing the last node is always easier, we are going to swap the values in the root and in the last node, and we will remove the last node instead. Now the minimum value is removed, but the problem is that this is not a min heap anymore. So what we will do next is start from the root, and for as long as the root doesn't satisfy the min heap property, we are going to swap it with the minimum of its two children. Think about it. For this to be a min heap, the root should always be less than or equal to its children. And if the minimum between the two children is less than the root, then that child should actually be the root of the heap. In this case, the minimum between the root's children is 7, and 7 is less than 9, so we are going to swap these two. Then we will continue to check the condition from that child. It only has one child, which is 10. and 10 is greater than or equal to 9, so the property is satisfied, and this is indeed a mean heap. Let's say we want to remove the minimum again. We will swap the values of the root and the last node, which is 10. Then we will remove the last node. Then we will start from the root, and for as long as the current node is greater than the minimum between its children, we are going to swap it with the minimum child and continue the algorithm from that child. The minimum is 9, which is less than 10, so we will swap this too. And we continue from 10, which doesn't have any children, so the algorithm is finished and we have a mean heap. Let's recap. Each time we remove the minimum, we swap the values between the root and the last node. We remove the last node. Then we start from the root. And for as long as the current node has at least one child, and its value is greater than the minimum between the children, then we will swap it with the minimum child and continue the algorithm from there. In the worst case scenario, we start from the root and always move to a child until we reach a leaf. So the maximum number of steps our algorithm performs is the height of the tree. Now let's analyze the time and space complexities. For the time complexity, we have proven that an insertion and the removal operations are performed in big O of height time. But what is actually the maximum height of a heap? Because a heap is a complete binary tree, in the worst case scenario, on level 0 we are going to have one node. On level 1 we are going to have 2 nodes. On level 2 we are going to have 4 nodes, and so on and so forth. On level h, which let's say is the height of the tree, we are going to have 2 to the power h nodes. Because the number of nodes on a level should always be less than or equal to n, this means that 2 to the power of h is less than or equal to n, which means that h is less than or equal to log of n. So the time complexities for insertion and removal are both big O of log of n. And for returning the extreme element, we just have to access the root node and return the value there. So this is constant time. For the space complexity, we use a binary tree, which consists of at most n nodes, where n is the total number of insertions. So we use big O of n extra space. And this is how the heap works. I hope you enjoyed it, and I'll see you on the next lesson.